Hey everybody, today's video has a very short title. It's going to be about E. And I mean E as in the mathematical constant E, which is roughly 2.718. And it goes on forever. It's actually one of those irrational numbers that I've been talking about. So we can say that E belongs to the set of real numbers minus the rationals, as in it is not rational. So what actually is E? We're going to get into that today. Then I'm going to show an interesting proof with E that involves calculus. What actually is E? The best way to think about E is that it's a number heavily tied to interest and interest calculations and a certain way that functions can grow. When a function grows exponentially, it means that the amount that it's already grown actually has a direct impact on how much it's about to grow further. Exponential functions kind of look like this, which is not to be confused with a parabolic function. So this might be something like y equals 2 to the x. It could be y equals 3 to the x. And specifically later on in this video, I'm going to talk about y equals e to the x and why it's special. So what actually is E? Well, let's imagine you take out a loan and that loan's going to create interest. It doesn't actually matter how much the loan is. Let's just say, to make things simple, you're going to be loaning $1. And the bank needs to make money off that $1. So let's just say the bank is going to charge you 50% interest twice. And this timeline is going to be the whole year. So this is an entire year worth of time. So this is January 1st and this is December 31st. You're going to have to pay 50% interest 2 times. So in the middle of the year, if your loan has 50% interest added to it, it's now going to go up to $1.50. And now at the end of the year, when we add 50% to it, it's going to be whatever $1.50 plus 50% of $1.50 is, which is going to be $2.25. And hopefully you can see that's because that's the same thing as saying 1.5 times 1.5. Now, what if the bank wants to do a similar thing, but they want to charge you interest at a higher frequency? Let's say that instead of charging you 50% twice, they charge you 25% interest 4 times. So quarterly now. So we're going to get charged 25% interest just before April Fool's Day, then again in the very middle of the year, and then again at the start of October, and then again at the very end. It's going to be a similar calculation. So how much money are we going to have here? Well, it's going to be $1 plus 25% of $1, which is $1.25. And now here, it's going to be whatever that is, plus 25%. I'm just going to calculate that somewhere else. So it's going to be $1.25. It's going to be 1.5625. It's going to be a crazy number, and the number's going to get more and more crazy. I'm not going to finish the calculations. Let's try and generalize. Another example would be, what if they charge you 1/12 interest every month, or 1/365th interest every day? The point that I'm getting at is that these increments can be smaller and smaller and smaller. Generally speaking, let's say we charge interest n times at a rate 1/n, which is what I've been doing so far. If we start with $1, we're going to be basically timesing 1 plus 1/n by itself n times. I hope this makes sense. So the first time when n was 2, I had to do 1 plus a half squared, which is how I got my 2.25. And in fact, now in my case with 4 increments, it's going to be 1 plus 1/4 to the power of 4. And let me just calculate that real quick. So it's going to be 5 over 4 to the power of 4. It's about 2.44. And in fact, that's because it's the same thing as saying 5 squared over 4 squared. Yeah. Oh no, sorry, that's not true. It'd be 25 squared over 16 squared. Anyway. If I raise it up again, I make n into 8, 16, doesn't matter. I keep making it bigger and bigger and bigger. This number is going to approach something. And formally, I can only really talk about this in terms of a limit. So I'm going to say the limit as n approaches infinity of 1 plus 1 over n to the power of n. So what does it mean to be charged interest infinite times at an infinitely small rate? Well, that's all that we're doing when we approach with this process. Essentially what this means is that I'm being charged interest at every rate. At every possible instant, I'm getting a little bit of interest. This is going to come out to e. So as n gets bigger and bigger and bigger, this number gets closer and closer to e. And if n could be infinity, which it can't be, we would reach exactly e. This is the definition of e. And this is why it shows up all the time when we talk about exponentials and interest calculations. Banks are going to use this number sometimes. So that's what e is. And I might just quickly rewrite the definition of e up here because we're going to need it later. So e equals the limit as n approaches infinity of 1 plus the reciprocal of n to the power of n. This is what e is. That's how we define it. Now, let's talk about a really interesting function, e to the x. E to the power of x. Kind of looks like this. We haven't really touched on calculus before, but I'm going to show you that e to the x, so if f of x is e to the x, e to the x is its own derivative. F of x equals f prime of e of x. So if I derive e to the x, I get e to the x. And it's very, very unique in that way. If I put any other number here as my base, it wouldn't work. Only e works. And I'm going to show why. So calculus is all about slope. All about gradient. If I draw my graph, a derivative function is going to take any value x, and we'll call this x1, and map it to some value f of x1. And it's basically asking for every value I can pick of x here, what is my gradient going to be? What's the slope at this point? So if I nudge x1 up a little bit, my gradient's going to change. Something like this. If I bring it down a bit, my gradient's going to get more flat. Basically, a derivative, f of x, is asking what is the slope of my graph for every value x. Now, there's a lot of ways that we can do this, but one way that we can do this is what's called differentiation by first principles. And that is to take that exact definition of differentiation and prove it that way. So let's just say, for example, I've got some value x1 that I want to derive. I need to find the tangent at this line. But I can't do that because it's just one point. In order to find the slope of something, I can do it with 2 points easily. I can pick a point here and I can speak about the slope of this line. That's fine. But this is not going to be the same thing as my tangent here. The line is a bit off. The key idea here is that as this point gets closer to being in line with x1, this tangent is going to get more and more accurate. So let's pick some other point. Let's introduce some distance d. And let's say this is x1 plus d. And we're going to consider where that hits my function. And obviously out here, we're going to be left with f of x1 plus d. And now let's investigate the tangent. Now, this is obviously going to be very inaccurate. This is not at all going to be my tangent at this point. It's just way too different. But as d gets closer and closer to 0, this tangent's going to get more and more accurate. So let's try and formalize that idea. Well, what is the tangent of this line? Well, we know from high school that the tangent of a line, you can calculate it given 2 points with something called the rise and the run. I think rise over run is the way of putting it. What is my rise? Well, it's the difference between f of x1 plus d and f of x1. Hopefully you can see that this is just going to represent this difference here. And what is my run? It's whatever this gap is, and this is a gap of length d. So I end up with this over d. And again, I want to analyze what happens to this equation as d approaches 0. Alright. So we know what the function f of x is. It's going to be e of x. That's the function that we're interested in. So let's just sub all these things in. So it's going to be saying e of x plus d, and I'm just going to use x in the general, minus e of x over d. And we're saying that this is going to approach the true derivative of f of x, the true tangent, as d gets closer to 0. Cool. So let's do some stuff with this. Well, I notice that in my numerator, we have a common factor of e to the x, so I'm going to take that out front. We end up with e to the x times e to the d minus 1 over d. And now remember, we're saying that e to the x is its own derivative, and that e is the only value that this is going to work for. So if e to the x is its own derivative, this whole thing is equal to e to the x. And I'm basically going to try and solve for e here, to show that this is only true for our value of e. So we end up with e to the x equals e to the x times e to the d take 1 over d. Well, we now have a common e to the x on both sides, so let's cancel those out. And we're actually going to be left with 1 equals e to the power of d, take 1, over d. And again, all this is as d approaches 0. It's important to emphasize that. Alright, let's jump over to the other side now. I'm going to jump here, and I'll rewrite that here. So we've got 1 is equal to e to the power of d, take 1 over d as d approaches 0. Let's do some more algebra. Let's times both sides by d. So we've got d equals e to the power of d, take 1. Let's add 1 to both sides. D plus 1 equals e to the power of d. And now this is kind of the weird part. We're going to take the dth root of both sides. So you should be familiar with the idea that if I have x squared, I need to take the square root. If I take x cubed, I can take the cube root. So for any general value, something to the power of d, I'm going to take the dth root. So if I take the dth root of both sides, I end up with e equals the dth root of d plus 1. Now my power rules tell me that the dth root of something is the same thing as that to the power of 1 over d. So I'm left with this as d approaches 0. Alright, now I'm going to rub out this side and go back. So we have another definition for e now. We have that e has to equal the limit as d approaches 0 of d plus 1 to the power of 1 over d. Now I'm going to try and argue now that this definition of E is the exact same as this definition of E. In fact, they're identical. The reason they're identical is because I can just say let K equal 1 over D. Alright, so K is the reciprocal of D. That means that if D is approaching 0, K is approaching infinity. Because if I divide a number by smaller and smaller numbers, that number is going to get bigger and bigger and bigger and bigger. So if something's reciprocal approaches 0, the thing itself has to approach infinity. This is going to be 1 over... This is going to be like 1 over a half, 1 over a third, 1 over a quarter. It's going to go all the way down. And as that happens, as D approaches 0, this is going to get bigger and bigger and bigger, which means that K is going to approach infinity. So now I can sub in K in my definition. So remember, K is equal to 1 over D, which also means that D is equal to 1 over K. So plugging in this equation here, I can say the limit as K approaches infinity of 1 plus 1 over K to the power of, well, 1 over D is the same thing as K. And that is E. And now you'll notice that my two definitions for E are the exact same, except one uses K, one uses N. And this is a trivial difference. And that completes the proof. So we've now shown that if any function, sort of K to the X, is its own derivative, the only way that can happen is if K equals E. So this number that we talked about at the start, E, which is very, very heavily tied to interest calculations and the idea of growth, exponential growth, also just happens to be the one number such that when I raise it to the power of X, it equals its own derivative. So again, that's really interesting. So we've got a number that somehow came up twice and two things that seemed very different. And you come to learn that they're actually not very different at all, but I won't talk about that in this video. But yeah, that's all I've got to say about E. Thanks for watching, everyone. Cheers.